Hey developers, welcome to Devcovery. Today, we're bringing you the hottest open source projects trending on GitHub, so you don't miss any tech developments worth your attention.
Today we're taking a deep dive into a trending project on GitHub, TurboVec, a high-performance vector index that's exploding in popularity. It masterfully combines the raw speed of Rust with the simplicity of Python bindings, offering a powerful new tool for anyone building AI-powered search or recommendation systems. We'll explore why this project is a potential game-changer for efficient vector similarity search. What if you could take a 10 million document corpus, one that needs 31 gigabytes of RAM, and shrink it down to just 4 gigabytes? And what if, even after that massive compression, it could still search faster than FAISS? That's the headline for a project called TurboVec. But the twist is even bigger. It ingests vectors online, with no training phase and no rebuilds, even as your data grows. At its core, TurboVec is a Rust vector index with Python bindings, built on Google Research's TurboQuant technology. It's designed for two key scenarios: memory, hungry vector search, and privacy-sensitive RAG applications. The promise is simple: fast queries with a tiny memory footprint. And the numbers suggest it's getting some real traction. The project, developed by RyanCodrai, has already pulled in over 7,100 stars, with more than 1,500 of those added in just the last day. The fork count is nearing 700. In a crowded field of vector databases, very few can claim this combination: massive compression, speed gains over FAISS, and a design that's completely local and training-free. So, what problem is TurboVec really solving? Modern vector search runs into three hard constraints. First, memory usage explodes as datasets get larger, especially with float32 embeddings. Second, traditional methods like product quantization require an offline training step. This often means you have to rebuild your index whenever the data changes. And third, hybrid retrieval can be clumsy. When you apply filters after scoring, you're often forced into trade-offs between overfetching data and losing recall. Now, teams have found workarounds using custom FAISS pipelines, big RAM servers, and pre-filtering stages. But TurboVec's approach is different. It replaces data-trained codebooks with a data-oblivious quantizer. It enables online ingest, so vectors are searchable the moment they're added, and it folds filtering logic directly into the scoring kernel. The goal? Lower memory, lower latency, and simpler operations, all without sending your data to a third-party service. The design here is incredibly pragmatic. At the heart is a Rust core that implements TurboQuant and the performance-critical scoring loops. On top of that, Python bindings provide a small, friendly API for daily use. This gives you Rust-level performance without ever having to leave your Python workflow. The magic behind it, TurboQuant, is based on a clean idea. First, it normalizes each vector so only its direction matters. Then, it applies a fixed, random rotation, which makes every coordinate statistically predictable. With that predictability, a technique called Lloyd-Max scalar quantization pre-computes optimal bucket boundaries. For a chosen bit width, say 2 bits, you get 4 buckets per coordinate. 4 bits, you get 16. Your vectors are transformed from bulky floats into tightly packed codes. On top of this, TurboVec adds 2 key refinements. One is called TQ+, which calibrates each coordinate on the fly to maintain high recall even at low bit widths. The other is length renormalized scoring, which corrects for biases introduced during quantization at search time with virtually no extra cost. The raw speed comes from handwritten SIMD kernels. These kernels use Neon on ARM and AVX 512 on modern x86 chips to perform scoring directly on the compressed data. You can even pass an allow list of IDs to the search function. The filtering happens inside the SIMD loop itself, skipping entire blocks of data that don't match. This is a clever way to save cycles while preserving recall. So, who is this for in the real world? Think about developers building RAG applications on laptops, edge devices, or small servers where every megabyte of RAM counts, or teams that must keep their embeddings on-premise for compliance reasons. It's also a great fit for hybrid retrieval systems, where you might use SQL or BM25 for initial filtering and then use vectors to re-rank the top results. Basically, any team hitting bottlenecks with FAISS that needs a leaner index without a full architectural overhaul could benefit. Getting started is designed to be simple. You pip install turbovec, create an index with your embedding dimension and a bit width, add vectors as they arrive, and then query for your top K results. You can even filter by ID. For persistence, it's just a single write call to save the index and a load call on startup. Early community reactions have been largely positive. Developers are excited about the compression, shrinking tens of gigabytes down to single digits while matching or even beating FAISS on speed. The convenience of simple Python bindings over a powerful Rust core is another big plus, and its purely local, on-premise nature really resonates with privacy-focused teams. Of course, there are also some notes of caution. Some in the community are asking for more independent validation of the recall claims across different types of workloads. It's also important to remember that turbovec is an index, not a full-fledged vector database. It doesn't have features like clustering, replication, or complex metadata filtering out of the box. Looking at this with a critical eye, 3 potential risks are worth flagging. First, the headline performance really hinges on modern SIMD instructions. AVX, 5, 12, and Neon are where it shines. Older CPUs that fall back to AVX2 might not see the same impressive speeds. Second, the underlying theory is strongest for high-dimensional vectors. With lower dimensions, some of the core assumptions are less effective, which is hinted at in the project's own Glove benchmark results. And third, scope is important. turbovec isn't trying to be a Milvus or a Qdrant. This means distributed operations, rich metadata queries, and multi-tenant management are all things you would have to build yourself. Despite these points, the outlook is solid. The project's simple architecture, training-free model, and efficient filtering make for a compelling tool that can easily slot into many existing pipelines. In the end, turbovec distills a powerful idea into a sharp, focused tool. The philosophy is clear. Compress aggressively, search directly in that compressed domain, and keep the operations simple. If memory constraints, latency, or data privacy are holding back your RAG roadmap, this index is absolutely worth a serious trial on your own data.
That's all for today's Devcovery. We hope these GitHub trending projects spark some inspiration for your development work. You can find all the repos mentioned in the description below. If you enjoyed this episode, don't forget to subscribe to our channel. See you tomorrow at the same time.